So putting these two ideas together, we have the fundamentals of any particle accelerator. And the first particle accelerators were built were generally linear accelerators. Basically, these use electric fields then to accelerate particles to higher speeds. And then we can have them involved in collisions to find out about the nature of these particles and so on. So here's a kind of simple example of that. And we've got negative particles in this case. And basically, if you look carefully as it makes its way through, we oscillate, we reverse the polarity of the sign on these cylinders so that we're always attracting it towards the next cylinder, making it move faster, accelerating it. You can pause that each time in between, so get repelled here and attracted there, repelled, attracted, repelled, attracted, repelled, and so on. So the acceleration takes place between the electrodes, and the electrodes, particles just leaving the node negative, and the one it's moving towards is positive. And since the particle is gaining speed, each electrode is longer than the previous one because your oscillating power supply is fixed in frequency. So as it's traveling faster, then you have to allow a longer distance for it before you're reversing the polarity. And then, for instance, once it's been accelerated, it could then, for instance, be deflected. You could use another electric field to deflect it left to right, or up and down in this case, and onto a target for collision as well. We can play again for that. In practice, we wouldn't do this with a single particle, and we would do it with bunches of particles, and we use the magnetic fields to keep the particles along central lines in reality as well. And to give you an idea, the SLAC in California is 3.2 kilometers long, with lots of accelerating bits. Due to the speed of light, incidentally, relativistic effects have to be taken account of, and that can adapt the values required.